energy transformations and the law of conservation of energy. It's a big title. Basically, the law of conservation of energy tells us that matter is something, or energy and matter. It could be the law of conservation of matter, the law of conservation of energy, the law of conservation of mass. They all mean the same thing. And it basically means that in a reaction or a transformation, the total amount of energy is going to be the same at the beginning and at the end. It's never going to suddenly increase or decrease without you being able to keep track of where it went. So it's kind of like the accounting system always has to add up. Okay? And by transformation, of course, we mean when one form of energy changes into another. So for our purposes, we're going to look at the simple transformation between kinetic energy and potential, gravitational potential. And to do this, we're going to imagine a falling ball. So let's take a ball, and let's say that this ball is going to be starting off being held still at 3 meters off the ground. So what we can do is we can describe the initial position of the ball. We'll call it position number 1, and we can talk about the kinds of energy the ball might have. It definitely has gravitational energy because it has 3 meters of height. So the gravitational energy that the ball has is mgh, we learned that. And that would be the height at position 1. And if we look at the kinetic energy of the ball here, because it hasn't been dropped yet and it hasn't started to move, it has no speed, so it has no kinetic energy whatsoever. But as the ball moves, as it falls down, let's take a look down here at the bottom. We'll call it position 2. Just before the ball hits the ground, right here. So it's falling down. Of course, it would be moving very fast. So if we look at the gravitational energy, well, if we're measuring from the ground, it's basically on the ground, so it has lost its gravitational energy, but it has gained kinetic energy, because now it has speed. So what we see here is a trade, and this would be the speed at position 2, so I'll put a little 2 there. It's a trade-off where the height has been traded for speed, but the total amount of energy is still going to be the same. All right? So let's see if we can describe that like this. Let's say that the total energy at position 1 is equal to the total energy at position 2. This is the law of conservation of energy in short form. They have to have the same amount of energy. Now, of course, that's what we call a closed system. Those of you who've taken chemistry, you know what an open and a closed system is. A closed system is one where nothing can come in from the outside or nothing can escape. No energy is added in or lost, so the energy stays the same all the way through. An open system is one where there could be energy escaping or energy added in. If I put a little jetpack on the ball, and the ball suddenly turned on its jetpack, well then that could suddenly be extra energy in the system that wasn't there before, right? So we could account for all that in the bookwork, but it would be kind of difficult to do. So we're going to consider this to be a closed system where just the ball is falling and nothing else is adding or subtracting from it. So this is the law of conservation of energy. Well, let's look at position 1. We're going to have some Eg and Ek. These are the two things we're comparing. So we'll put them in. And these will be the position 1, gravitational energy and kinetic energy. And at position 2, there will be a different gravitational energy and a different kinetic energy at the bottom. Now this is kind of like the net force equations. There could be many different kinds of energy involved in the transformation, and you would just list as many as you had here, right? But we're going to deal with just these two for now to keep it simple and learn the concept. So the gravitational energy at position 1 would be mgh. We've already learned that, and it would be the height at position 1 that would matter. And the kinetic energy at position 1 would be 1/2 mv1 squared. So I'm just putting in the formulas. The gravitational energy at position 2 would be mg times height number 2. And the kinetic energy at position 2 would be 1/2 mv2 squared. So far, we're just writing in the stuff that we've already learned. Now let's see if we can put some numbers in it. At our position 1, we have a mass. Well, actually, look at this right now. Look at this. Look at every single term in this little equation. You'll see there's a mass present in them all, which means the mass can be divided out of every term, and we don't even need to know the mass at all. Okay? So then we can fill in the numbers we have. 9.8 for G, right? And the original height is 3 meters. It's important when you put your H's in to remember that they're always measured from the ground up. And if they ever give you one that's not, you have to kind of convert it to how much up from the ground. H stands for height, which is always thought of as how high above the ground. We don't often think of our height as how far below you are, right? So height above the ground is H, always. So think of the ground as your zero level. Then we have plus 1/2. Initially, there is no speed, so that's going to just turn into 0. But later, when we get near position 2, near the ground, we have lost all of our height, and the height becomes 0, and now we will have a certain speed. So we can use this equation to figure out what that speed would be, because it's the last thing left. So this, I think, is 29.4, and that's a 0, and that would be a 0, and we would get 1/2 v2 squared. It comes out pretty simple. If you multiply both sides by 2, you get 8. 9 is 18. 58.8 equals v2 squared. And if you think about it, think about the squares on either side of 58. Right? There's 7 squared is 49, and 8 squared is 64. So that's going to be somewhere in between those two, but a little past halfway, right? So I'm guessing that's about 7.7-ish, give or take. So V2 would be around 7.7 meters per second. Let's fix that up, meters per second. So we could use this to figure out the speeds. In fact, we can use this to figure out how fast something is going at either spot, here or here. We could use it to figure out the height of something, here or here. We could use it to figure out both speeds and heights. Okay, let's take the same scenario and do another example. Let's take the same ball, and let's drop the ball, and it'll still be 3 meters. But this time, instead of dropping the ball all the way to the bottom, let's figure out what happens when the ball starts here and falls to this spot right here, which will be, let's go 1 meter off the ground. So that is our new position 2. So now we have position 1 at the top, and our position 2, I'll put in black here, is going to be what happens at 1 meter off the ground. At that point, the ball is still moving, and it also still has height. So watch what happens. If we take the statement that the total energy at any one spot in the whole motion of this ball must equal the total energy at any other spot in the whole motion of the ball, and the total energy is made up of kinetic energy and gravitational energy in both places, then we can write our formulas in 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2. And the m's are going to cancel out of the expression because every term has an m, so we don't need to know the mass. And then we can just write in the numbers that we know. Well, at the beginning, we have 0 speed, so that turns into 0. But we do have height at the beginning, 9.8, and it's 3 meters high at the start, position 1. Our new position 2 has some speed. That's what we're going to figure out, how fast it's going. And there will be some height as well. But the height there is only 1 meter off the ground, so we put the 1 in. And then we crunch the numbers. Again, we get 29.4 equals 1/2 of V2 squared, but this time we have plus 9.8. So I have to take that over to the other side and subtract it. So what'll that be? 19.6? Right? Correct me if I make a math error here. Oh no, isn't it 18? No, it's 19, that's right. V2 squared. Multiply both sides by 2. Don't fall into the, don't make the mistake of dividing both sides by 2 when you see that half there. You either want to divide by a half on both sides or multiply both sides by 2, double them, right? So this would be 12, 9, 9, 18, 19 to 39.2 equals V2 squared. And 5 is 25. 6 would be 36, and 7 would be 49. This is just a little bit bigger than 36. So, you know, I always go like 36, 49. Where am I? I'm at 39.2. So that's about halfway is 0.5. So I'm going to say this is about 6.3-ish or 6.4-ish. How does that sound? 6.3? 6.3. See how you can estimate square roots like that if your calculator happens to break or you're stuck. So 6.3 meters per second is the speed that you would get at that point. Right? So you can use this little equation, this thing that I've set up right here, as a way to describe any sort of energy change if it involves kinetic and potential energy. Let's do another example, one more maybe. This time we'll do an example with a roller coaster. So let's say we'll draw a picture of a roller coaster. Let's say you start here and the roller coaster goes down, then it goes back up, and then down, and that's the end of the ride. Kind of a sucky roller coaster. So we'll call this the ground, this level right here. And then we'll call this height up here, the original height. Let's call that 30 meters. Here's your little railroad car, your roller coaster car. At the very top, as it comes over the top, it has very little or no speed. So again, it has no kinetic energy at the start. It has only potential energy. What we're going to do is we're going to look at two spots. We're going to look at the spot right here. We'll call this position 1. Actually, no, we'll call that position 2, because the original position is position 1. So that'll be spot number 2. This will be spot number 1. And then we'll do spot number 3, which would be sort of, how about right here, the top here. Okay, so I just need a second. I got to make sure the numbers will actually work. So say that, and then if I divide that by... Okay, so what we're going to try and figure out is what this height will be right here, and how fast the object is going when it gets to right here. Okay, but in order to do that, I have to tell you a few other numbers. So let me move that over. I'm going to tell you that this particular height is going to be, well, let's call it 18 meters high. And we want to figure out the speed here. And then I'm going to tell you that this is going to be the height, and I need you to figure out the speed. But in order to do that, I have to make sure that it works. So give me 1 second. Okay, let's say that the speed at this point, position number 3, the speed is going to be 8 meters per second. And we'll see how fast. Actually, maybe I'll make that even a little bit smaller. 4 meters per second, just so that it doesn't look funny. Okay? So we're going to use our little expression. We're going to use it twice. We're going to say that the total amount of energy at any one position is equal to the total amount at any other position. Now, the 1 and the 2 just mean any 2 spots. It doesn't always have to be the first spot. Okay? A lot of the examples we do, we start with the first spot. The reason we start with the first spot is because we often know the most about it. We know everything about this spot. We know the speed is 0 and the height. So what you're looking for, one of these 2 things that you're starting with has to be something you know both things about, or at least the most about. So look for one of the positions where you might have the most information and call that your position 1. It doesn't have to be the first position or the second in order. It's any 2 spots. So you choose a spot where you know lots of stuff to help you find out about a spot where you know less stuff. That's basically how it works. So what do we write here? Well, we know that we're going to have 2 kinds of energy, kinetic and gravitational at position 1, and the same is true at position 2. So we can automatically write this every time. Then we know that kinetic energy is 1/2 mv squared. Oops, that'll be v1 squared, sorry. 1/2 of the first speed squared plus mgh1. This will be 1/2 mv2 squared plus mgh2. Remember, the heights are always measured from the ground up. Okay? If you measure from up to down towards the ground, like how far it falls down, then you'll end up describing energy lost, which doesn't fit into this equation. So these heights all have to be measured from the ground up. Each of these terms represents an amount of energy the object has, not the energy that it may have lost. Okay? Very important. Okay, what is the initial speed? Well, it's 0. So, and again, the masses can cancel out. I don't even need to consider them. Okay? So this will be initial speed of 0. So that's going to disappear, and the initial height is 30 meters. So you see how I know all the numbers for that position. The next position was position number 2. We knew the height was 18 meters, but we didn't know the speed. So let's find out the speed. v2 squared and 9.8 times the height, 18. And then we just crunch the numbers. Question? The angle. What angle were you thinking of? The angle, no. Because all we're doing is we're taking a picture when it's right here at the start, and we're taking another picture when it's right here, and we don't care how it got there. Right. That's a good point. Let me finish this, and I'll go back and show you the cool thing about energy. Because energy, of course, is a scalar. It has no direction. So the direction that you use to get to where you're going is irrelevant. It's just a comparison of the beginning and the end, and in between doesn't matter. Anyway, let's finish this up. So this will be our 294 this time, right? Plus 1/2 v2 squared, and then 18 times 9.8. That's about 176-ish. 0.4. So I'm going to have to bring that over and subtract it with the 294, leaving 117.6 equals 1/2 of v2 squared. And then if you multiply both sides by 2, let me just kind of jump over here. That will turn into 235.2 equals v2 squared. And if you take the square root of that, you're getting somewhere around 15.3-ish. For the speed. So you'll be going pretty quick when you get down there. 15.3 as you pass through position number 2. Now, before we do position number 3, well, why don't we do that first? Position number 3 will be the same thing, so let's do one more. See how the pattern is emerging. Now, we can use position 1 and position 3, or 2 and 3. Question?
From 17.6.
117.6.
Yeah.
Multiply both sides by 2. Right? to get rid of the half. Gives you this, and then take the square root. Okay? So we're going to do it again to answer the next question, but the key here is I can choose whatever I want for my position 1 and 2. Or 1 and 3. I can use 1 and 3, I can use 2 and 3, I could use 1 and 2, whatever. I'll have to use 3 somewhere because I need to figure out something about 3. But I already figured out 2, and I know everything about that now also, so I could compare positions 2 and 3 as well, as long as I know everything. But position 1 is the easy one because it's just potential and there's no kinetic, so it's easier math. And it's given, so in case I made a mistake, I don't carry that mistake forward. So I'll choose to use position 1 again. So the kinetic energy at position 1 plus the gravitational energy at position 1 equals the kinetic energy at position 3 now, and the gravitational energy at position 3. And this would be 1/2 mv1 squared plus mgh1, and this would be 1/2 mv3 squared plus mg height at 3. And we put in the numbers that we have. And if we go back to check, the only number they gave us was the height, which I think was, they gave us the speed, 4 meters per second, and they want us to find the height now. So we put in all the numbers that we know. We've already seen that there's no speed, so this becomes a 0 at the start, plus, and the m's, of course, are going to cancel out, so we can cross out the m's. You can only do that if there's an m in every single term, okay? But with these particular kinds of transformations, it happens a lot. 9.8, the original height at position 1 was 30 meters. 1/2, this time they told us the speed, it was 4 meters per second, so I'll put that in for the v, and now 9.8 and h3 is left over for us to solve. That's the only difference. But we can do that because we can do the numbers. So 294 equals, this would be 16 divided by 2, so it becomes 8, and this becomes 9.8 h3. So we take the 8 to the other side and subtract it, so that would be 286, and that would equal 9.8 times h3, and if we take 286 and divide it by 9.8, we get 29. So actually, it's not much of a difference. I should have made it go a little faster. 29.2 equals h3. So in reality, we only fell 0.8 of a meter. So we'll go back. My picture's off a bit. I should have stuck with the 8 I had originally thought of, but that doesn't matter. This second bump would actually be much closer. It would actually be up a little, almost to the top, right? Which brings up another thing. Now that you see how this works, you would realize why this particular kind of roller coaster is impossible. Right? Because if you start here at the beginning and you have mgh, then the total energy you have is based on this height only. And if you go down to here, you can turn that into speed, but as you go back up, you'll turn it back into height. And if you turn it all back to height, then you'll get to the same height you were before, because the energy can't change the total amount, right? Which means there's no way you could go higher. So if you rolled a ball down this ramp, it would never go higher than that line. So this roller coaster could never work. Unless, of course, you put a jetpack on it and gave it extra energy, but then it's an open system and it's not closed anymore, right? Well, that's a good point. If we brought in friction, then what would happen is this total energy you started with, as you went down, there would be a loss of energy. The energy, it would be heat energy from the friction, right, on the wheels. So when you tried to go back up, that loss wouldn't be there. It would be gone as heat. And that means you wouldn't even be able to get to the full height that you started, because this would represent the loss of the friction energy. But for our questions, we just consider that to be negligible for right now. But you could factor that in, right? So in real life, a roller coaster would not even be able to go as high as it started. It would always be a little bit less because of the friction. Now, the other thing you asked, Kevin, was about the angle and how you get there. Interestingly enough, if instead the roller coaster could somehow do this without like if it could roll down and go like this all the way down, it would not change a thing. Because I'm still starting here with the same numbers, and I would still be in position 2 with the same numbers. In fact, when you're dealing with energy, the path that you take between the positions is completely irrelevant. Okay? As long as it's a closed system and no extra energy is gained. So you could also think about a bird flying. That's kind of a good example. Now, a bird who's flying, is that a closed system or not? Well, let's draw a couple of pictures and see the difference. A bird who's gliding with his wings open but not beating the wings could be a closed system, because the bird would glide down, right? And then it could use its speed to soar back up. But just like a roller coaster, it could never go higher than it started, right? It would always end up at lower. So a glider does this, right? If you were just to glide, you could follow this path, but you'd always end up you'd never be able to go higher. The only way you could go higher is if the bird were to beat its wings and add muscle power, which is an input of energy that would make it an open system. See what I mean? Or if there was rising warm air over a highway that the bird could hit, that warm air could maybe give it a boost and bring it up. In fact, lots of birds glide over highways because they glide up on the warm air. But that's not a closed system, because that's extra energy being put into the bird. A bird who's just gliding is kind of like a paper airplane. It just it floats, but it never gets to go back up higher than it started, right? So the path doesn't matter. Okay, and that's really the gist of this whole thing. I hope you will use this particular method at first. There are shortcuts that you can take. You can look at this as your pattern for solving these questions, but there are shortcuts you can take. For instance, in the first example, you could look at it once you get the idea, and you could say, oh, wow, let's go way up to the very first example of the ball. You could say that at the top it had all gravitational, and at the bottom it had all potential, all kinetic. So you could look at this scenario, and you could simply write, I'll squeeze it in here, you could simply write that at the top it was EG, I better get this right, and at the bottom it was EK, and all the EG turned into EK. And you just get 1/2 M, I'm all backwards, sorry. Everything was going well until I switched to blue. MGH1, and this would be 1/2 MV2 squared. You could get right to there, but that's what we did, right? Because look, MGH1 is right here, and 1/2 MV2 squared is right there. So you could use this, and you could skip to that. Once you get the hang of it, you'll recognize some shortcuts as you go. The other thing I want to show you is that some textbooks will show you a slightly different way of presenting this. And if you happen to Google this and study it online, which nobody of course will do, but you might, right? You might see it presented a different way, but I want to show you that it's really the same thing. So I'm going to go past all my stuff here, all the way to the end. Why don't we just erase this little picture. And what some books do is they state the law of conservation slightly differently. They say that the change in gravitational energy will equal the change in the kinetic energy, which is what we said, right? If one goes up, the other goes down. But the problem with this is when you write it down, you would get MGH2 minus MGH1, right? That's EG2 minus EG1. And I said 1 and I wrote 2, so I'll fix that. EGH1. And on the other side, you would get 1/2 MV2 squared minus 1/2 MV1 squared. If you put the 1's together and the 2's together, you would, if you bring that 1 over here, you'd get 1/2 MV1 squared minus MGH1 equals 1/2 MV2 squared minus MGH2, which looks almost like our equation, except these are minuses instead of pluses. And the reason for that is because some of these changes are gains and some are losses. And so the minus sign is not distinguishing whether it's a gain or a loss. Like for instance, you're going to lose height. So you're going to lose MGH1, right? and you're going to gain speed, so you have a positive V2. This would be considering the energy as gains and losses, which is harder to determine, I find. It's harder to tell who's losing and who's gaining. So the way I do it, everything represents the amount of energy something would have at that point, not how much it may have lost at that point. See the difference? So this one requires you to keep track of losses and gains in order to make sure you get the right signs in there. Whereas the method I use, all you have to do is come up with a description of how much energy they actually have. This is the energy it has at position 1 that's kinetic. This is the energy it has, energy it has, energy it has. None of these represent energy lost, which is why you must always measure your heights from the ground up when you do it this way. But anyway, that's the gist of it. And now you can go to the worksheet that I gave you before, and there's about 4 or 5 questions called energy transformations, I think, and you can practice this kind of thing.